Hello guys, in this last little lecture series, I wanted to give you a little bit of a head start into calculus and get into some of the basic ideas that you're going to be covering as you begin calculus either in the summer, next semester, or whenever. So there's three main components of calculus, some of which we've already discussed a little bit about, but the three main mathematical concepts you're going to be focused on were called limits, derivatives, and integrals, usually done in that order because they build upon each other. Limits describe behavior as we approach something, which is very similar, and we actually discussed that at the very beginning of the semester, like what's the limit as x approaches infinity? Is just another way of just saying, well, what's the end behavior of a function, or what's the limit as we approach an asymptote from the left or from the right? Is it going to infinity or negative infinity? But the idea of a limit is very important in calculus, and to define it mathematically. The derivative is kind of the algebra of the derivative is what I wanted to get into this video because it's something that we discussed a lot of that algebra in chapter 2, and I just wanted to do a little refresher um, as and define what we call the difference quotient, something that we didn't really have time for back when we were getting into chapter 2. But one of the key problems in calculus is finding what we refer to as a tangent line. So and these are actually my lecture notes, my lecture slides from my calculus class, but I just wanted to sort of set it up. But what we're often looking for is, like, say for example, we're climbing a hill. Like imagine that there's a guy climbing up this hill here, and he stops at a very particular point. And let's say he wants to know, well, what is the slope of the hill at this particular point that he stopped at? Like, how steep is this incline? Like, say he's over here, right? It's a steeper point on the hill is steeper here than it is here, and we can imagine what we call the instantaneous slope as being, well, what's the slope at this specific point, and how do we calculate that? Now, mathematically speaking, this is what's referred to as a derivative, and a derivative of a mathematical curve will come up with what's called a slope function. But the math that goes into finding that is a little bit tricky, and this is the main idea of what we're trying to find and discuss in this section. So let's go ahead and get back to the lecture notes, which are going to be a new little mini 2-page packet for this section. Okay, where am I at? But basically, let's start off with defining the average rate of change, which basically describes what is the slope in between 2 points. Because, like say for example, we're looking at what's the slope of this parabola between, at this point in time. We could use what we call an average slope to figure out, okay, what's approximately the slope of that point. Notice that this would not give me the exact slope at either one of these points, but will give me a similar steepness to the point as a whole. And basically, the idea is if you take an average, it's not exact, but there's a way of determining, okay, what is making it more exact as we go. But basically, the average rate of change is defined to be is given to you in the little box on your packet. But it says the average rate of change is equal to the change in y over change in x. Or if I'm looking at it, I can kind of imagine this, since it's a triangle, and again, by Pythagorean theorem, we could figure out what's the distance of that line. Though we'd notice that we don't really care about the distance, we care about the slope. We care about the steepness when we're trying to figure out the tangent problem. And really, since this is just it's a line, it should be a linear equation, we know that the slope should be equal to the rise over the run, aka the change in y, delta y over delta x. But if we're talking about a mathematical function, we would often write it in this alternative form, f of b minus f of a, where if a describes the x location of this point and b describes the x location of the secondary point, f of b would give us the height here, and f of a would give us the height right here. And so if I do f of b minus f of a, that would give me the rise in this line, and the run is simply going to be b minus a, the distance between those 2 points. And basically, if I can figure out this value, f of b minus f of a over b minus a, this will give me the slope, aka rise over run. So this formula is nothing really new. It's just if we're talking about a mathematical function and we want to find the average rate of change, it's just an alternative, it's just a different way of saying the same thing. So let's say we wanted to take this parabola and find the slope of these two lines. We could phrase this a different way by saying, find the average rate of change between x is equal to 1 and x equal 3. Basically, on average, how much is this function changing over that interval? And one of my recommendations is, like, we could just pick one of the pick which of these values are A and B, but essentially it's like, well, usually A is the left point and B is the right point. Basically, that's what A and B are in the formula. And if I want to find the average rate of change is equal to f of B minus f of A divided by B minus A. And I could just plug in B and A into the formula. And basically, B is just one of my positions, 3. A is 1. B is 3 and A is 1. And this would give me a formula for the average rate of change. And as I'm reading this, essentially, really what this is another way of saying is, well, f of 3 is just the y value, which would be this point. And f of 1 would be this point. And again, on the bottom, this is just another way of saying y2 minus y1 over x2 minus x1. But with a mathematical function, if I want to find the y value, that's the same as just plugging the input into the x value, right? Because input gives me output f of 3. Mathematically speaking, I could calculate that by just plugging in 3 into f of x, because f of x is this, so f of 3 must be, well, 3 minus 3 squared is 0 squared, which is 0. And then f of 1 would mean to plug 1 into f, which would be 1 minus 3, negative 2 squared is 4 over 3 minus 1. Or if I'm looking at my graph here, I could see that y2 is 0, y1 is 4, x2 is 3, x1 is 1. So in an alternative form, I could just do y2 minus y1, x2 minus x1. But it's the same formula, it's just phrased for a mathematical function instead of a line. And then, obviously, I could find the slope by just doing a bit of quick math. Well, it's minus 4 over 2, aka negative 2. And that would give me the slope of the average rate of change between those points. But basically, that's synonymous to the slope of what we refer to as a secant line, which does kind of have to do with trigonometry. Really, it's Latin. Secant comes from secans, which means to cut in Latin. I'm not a Latin expert, but that's as far as I remember. Anyways, or you could just do rise over run. Rise, it falls 4, runs 2, and that would give us our slope. But another thing about the average rate of change is it's always dependent on the interval, because the slope between these 2 points would be different than the slope between another 2 points. So if I were to take the average rate of change on a different set of points, it would most likely give me a different result. Let's move to a fresh example, and then in the next video we'll talk about how this applies to calculus. But let's take another example of a linear function and see, well, what would happen if we were to apply the average rate of change formula here. So in this linear function, we have L of x is equal to 2x minus 7. And actually, if we're remembering properties of linear functions, remember that this is like mx plus b, our slope is 2, our y-intercept is minus 7. So we could kind of imagine what this line looks like and graph it. But you can find the average rate of change without a graph just by using the formula. So say we wanted to find the average slope between 2 random points. We could do this by applying the average rate of change formula, which would be L of 7 minus L of 2 over 7 minus 2. And also notice that the average rate of change here, I used f of x, but the function just depends on whatever your function is. So if we're going to change it to say L or H or G or A or whatever, notice how I'm using the same formula. I'm using L of 7 instead of f of 7, but it's the same idea, just dependent on what letter we're calling our function. And if I go ahead and do some math here, L of 7 would mean plug 7 in here. That would give me 2 times 7 minus 7, which is 14 minus 7, 7. And L of 2 would be 4 minus 7, which is negative 3. And notice how I'm using parentheses because it's this minus a negative 3. And so be careful that you're not losing a negative with your math. But what that would leave me with is 7 plus 3 over 5, 10 over 5, which is, of course, 2. But anyways, what I get is the average rate of change between 2 points on the line. But the thing to notice about a line, and why I'm doing this example at all, is that line had an intercept at minus 7 and a slope of 2. So, just by knowing the basic properties of a linear function, if I was taking the average rate of change between, say, 2 and 7, That's going to give me the slope between those 2 points, but the average rate of change should be equal to the slope of the line, because that's exactly what we're doing. We're trying to find the slope between 2 points, but since it's a consistent slope, the slope will be the same regardless of what I take. So if you apply the formula to the next bullet point and try this on your own, you should get 2 as well. Basically, it does not matter what you use for a and b, you're always going to get 2, since this line will always have a slope of 2. But in functions which are not straight lines, we get a variation in the slope, and that's why the tangent problem is a little bit more difficult. Because in a straight line, the slope is obvious, but when the line has curvature to it, the slope changes depending on where I'm at on the curve. But the last little example I wanted to do and end this video is, what if we apply the average rate of change formula more algebraically? Instead of picking 2 numbers, let's say we pick a position on this line, and let's just say we call this position x. Just as an arbitrary wherever location. And then we're going to look at, well, what if I move to the right, x plus h, if I go over by h, that would leave me at a position of x plus h on the curve. And it's sort of like, instead of using a and b, we're changing the variables to x as the starting point, and plus h as being to the right h from that position. Well, basically, this would be my a and b in the average rate of change formula, and the average rate of change between those 2 points would look like this. ARC is equal to f of b minus f of a, which is x, over b minus a. And basically, instead of plugging numbers into this expression, I'm going to plug in these particular algebraic expressions. And this might seem a little weird, but there's like a sense behind why, which I'm going to do in the next video. I'm going to talk about that. And this is actually what we refer to as the difference quotient, which is the fundamental definition for a derivative in calculus. And in the next video, I'm going to talk about why that'll make sense. But for now, let's just look at the algebra of what this means. But basically, what this is going to do is going to find the average rate of change between those 2 points defined by x and x plus h. And if I look at the algebra here, what I'm going to be left with is, well, in the numerator, I have L of x plus h, which just means plug in x plus h into L. So if we were to think about what does this L of x plus h mean, well, I know that the L function is that. So that would be, whoops, I accidentally clicked something on my tablet. I'm trying to, okay. That would be 2 times x plus h minus 7. Because, right, and this is an important thing about what does plugging in x plus h mean into a function, but remember, this is L of x. We're going to place that number right there. And if I have a multiple termed input into a function, the whole x will change, and we have to remember algebraic principles. So really what that would amount to be would be 2x plus 2h minus 7 for what does L of x plus h mean. So basically L of x plus h is all that. So if I'm trying to simplify my average rate of change, what I'm going to be left with is 2x plus 2h minus 7. And then it says to do minus L of x next. So this would be my L of x plus h. And then I have to then subtract L of x. Well, L of x, again, I'm not given a number here. That's what's a little bit trickier about this example. But algebraically speaking, L of x is just exactly 2x minus 7. I know what the function is, so I know that that's just exactly what I started at. 2x minus 7 was L of x. But something that's very important to remember here, which a lot of students often forget with the difference quotient, which is really why I'm getting into this right now, is to remind you the rules for algebra and functions when you're dealing with calculus. But basically, I have L of x plus h, which is this entire function in red, and the difference quotient says to do L of x plus h minus L of x, which means an entire function minus another entire function, which I should use parentheses here because I'm going to have to make sure it's being properly subtracted. Then in the denominator, I have x plus h minus x, which of course x minus x is 0, so the denominator just leaves me with h. But basically what we end up having here is, if I then apply the distributive property, what I get is 2x plus 2h minus 7. This would become minus 2x. This would become plus 7. And what you'll notice is there is a strong cancellation here because I have a 2x and a minus 2x, which of course cancels. And I have a minus 7 and a plus 7, which also cancels. So what I'm left with is 2h over. And of course, h is now a common factor in this fraction, which will now cancel and leave me with 2. But what I wanted you to notice is what I wind up with is even after this very generic series of algebra, I wind up with 2, which is going to be the slope of the line regardless. So even if I apply this weird expression here, a line will always have a consistent slope, which is why we say this line has a slope of 2. But when we're talking about parabolas, we don't refer to it as having a slope because it changes. But the part of the tangent problem is finding the slope of any function, but it all kind of starts with this math, which is the important thing. So in the next video, we will work on the back page of the packet, which is, I'll talk a little bit about the difference quotient, what that means and why, and we will do some algebraic examples of solving the difference quotient and using it to find what we call the derivative of a function.